Hello, everyone. Welcome back to this week's GOCC. Today we have Bruce Sagan from Michigan State University here to speak with us about the protean chromatic polynomial. Before we get started, let's remind ourselves of our community statement. We are all learning, everyone has something to contribute, and no one has all the answers. So, Bruce, with that, whenever you're ready.
Sounds great. And I love that community statement. Let me add to that by saying no questions are stupid. So please stop me at any point if you don't understand something. I want this lecture to be clear from beginning to end. So, and I'm going to and I want to thank Bailey for the invitation to speak. And I'm going to be talking, as she said, about this protean chromatic polynomial. So here's a outline of the talk. First of all, I will start and make sure that we're familiar with all the words in the title, to make some sense of that, and then I will talk about what the chromatic polynomial is, in case you haven't met it before, and prove some of its elementary properties in the second section. And one of the things that I love about the chromatic polynomial is that it has this tendency to show up in areas where it has no business a priori being. So I'm going to give you two examples of that in the third section, one having to do with acyclic orientations, and one having to do with hyperplane arrangements. Then in the fourth section, I'm going to talk about a very important topic of current research, which is an extension of the chromatic polynomial to something called the chromatic symmetric function. And we'll talk about that a bit. And then I'll end with some comments and a big open problem that maybe somebody in this audience can make some progress on. So, starting out at the beginning with the title, what does protean mean? You may not see that every day. It comes from the Proteus, who was the Greek god of sea and water. And so, right, water is changeable. It fits any container you put it on. So that's where it comes from. And here's an artist's conception of what Proteus might have looked like. I cannot verify that it's accurate, but it's a nice picture. And then chromatic here, despite the fact that I'm a musician, has nothing to do with music. Here we're talking about coloring. So there's a colorful annulus. Now, I'm sure I don't need to define the and polynomial, but it may not be clear what chromatic has to do with polynomial. So that'll be our first order of business, is to tell you exactly what the chromatic polynomial is. Okay, so G is going to be a graph. Let's see if I can get rid of this. There's this thing in the way at the top of my screen, and I'm not sure how to get rid of it. Yeah, okay. I'm gonna have to wing it sometimes because I can't see the top line of my slides. So tell me if what I say is not has nothing to do with what is up there. So G is going to be a graph with vertices V and edges E. And here's a particular example graph, which you should get up close and personal with because you're going to be seeing a lot of this graph during the talk. So it's got four vertices, U, V, W, and X, and then also four edges. One from, and can you see my cursor here? Is that, yeah,
Yes.
okay, great. One from U to V, one from U to X, one from V to W, and one from V to X. Okay, so typical combinatorial graph. And then a coloring of my graph is just a function C that takes each vertex V to a certain set, which we think of as a set of colors, if you like. And then we say that the coloring is proper if whenever we have an edge from U to V, the colors of its endpoints, U and V, must be different. So you're not allowed to have the same color at the endpoints of an edge. So for example, this is a proper coloring of that graph, our example graph, right? Because there's two blue vertices, but they're not connected by an edge, so that's fine. On the other hand, this is not proper, right? Because now the two blue vertices are endpoints of an edge. That's forbidden. Is it clear what proper colorings are? Because if it's not, you might as well not listen to the rest of the talk. Any questions about what it means to be a proper coloring? Okay. A thumbs up. Thank you, Joseph. Okay, great. So let's then define the chromatic number of G, chi of G, which is just the smallest number of colors you can use and get a proper coloring, right? Any guesses what the chromatic polynomial of our example graph is? Well, it turns out to be 3. Why is it 3? Well, I just displayed for you a proper coloring that has 3 colors, right? So you can do at least as well as 3. Why can't you do any better? Why couldn't you do it with 2 colors? Well, think of it. We've got this little triangle here. Can I use 2 colors to color the triangle? Clearly not, right? Since every pair of vertices is adjacent in the triangle, and there's 3 vertices there, I must use 3 colors on these 3 vertices. I can't get away with fewer, and so this is indeed the minimum that we can have. Everybody clear on what chromatic numbers do for a living? Okay, great. So famous theorem, the Four Color Theorem, proved by Appel and Haken back in 1976 when I was still a graduate student. If G is planar, that is to say, I can draw the graph in the plane such that none of the edges cross. So the example graph we have is planar for. Then the chromatic number is at most 4. Now this is a very amazing theorem from several aspects. First of all, it had been the four-color conjecture for over 100 years before it was proved. And in fact, there were at least 1 or 2 false proofs in the literature, proofs that were later shown to have errors in them. Also, it's kind of amazing that the chromatic number of these graphs is bounded. Why? Well, think about it. If I take n vertices and connect them all together, the chromatic number of that graph is n, right? Same argument that we gave with the triangle. So for general graphs, the chromatic number can grow without bound. Here, though, it can be at most 4. And the other thing that made this special was that this was the first proof that made extensive use of computer calculations. There were so many cases that needed to be checked that it couldn't be done by hand, and there were actually debates in the mathematical community at the time about whether we should accept this as a proof because it couldn't be checked by a human completely. I think nowadays there would be no debate, but right, this was a real new thing at the time. And so there's pictures of Kenneth Appel and Wolfgang Haken, both of them much older in these pictures than they were when they proved the four-color theorem. Now, I do enumerative combinatorics. Notice the chromatic number is an extremal invariant, right? We're asking for a minimum. I'd like to turn this into a counting problem so I can do enumeration. And for that, we define the chromatic polynomial of the graph, P of G or P of GT, if I want to be a little more specific, to count the number of proper colorings that I have using a set with T colors. Okay? So that's, you may be wondering, why are we calling this a polynomial? We will show in a second why it should be a polynomial, but we'll show kind of with this example why it might be called a polynomial. Let's take our example graph and let's color the vertices in order U, V, W, X. Right? Just go around the graph clockwise like that. Well, when I start off coloring U, I've got T choices, right? Because I can use any one of the T colors in my set. What happens when I get to V? Well, V is adjacent to U, which was just colored, and therefore I only have T minus 1 choices when I get to V, because I can't use the same color that I had on U. What about with W? same thing, right? W is adjacent to V, which was already colored. So I've got T minus 1 choices. What happens at X? Well, now X is adjacent to two vertices, and we know they're of different colors, right? Because U and V are connected. So there are two colors that are ruled out at X. And so the total number of colors is just going to be the product, right? You have to do all of one and the other and the other. So it's take product rule. And that's a polynomial in T, the number of colors. And as I'm fond of saying, that is not an accident. It turns out that P of G is always a polynomial in T for any graph, and we'll prove that shortly. But just let me make sure. Any questions about this example? Things clear. Okay. So, first thing we already noted, this is a polynomial in T. Secondly, it's closely related to the chromatic number. The chromatic number is just the smallest positive integer, such as that if I plug it into the chromatic polynomial, I will get something positive out. Why is that? Well, think about it. Suppose I plug in a positive integer smaller than chi of t, chi of g rather. Well, what is chi of g? It's the minimum number of colors you can use. So if I use fewer colors, how many colorings are there? Zero, right? Chi of g is the minimum, and therefore, since P of g is counting the number of proper colorings, if I plug in something smaller than the minimum, it's going to spit out zero because there are no colorings of that type. What's going to happen when you hit chi of g? Well, then, again, by definition of chi of g, there's at least one coloring with that many colors, and therefore, when I plug into this, the number of proper colorings, it'll count you at least one, so it'll be positive. Now,
Sorry about that.
Yes. Yes,
Is
go ahead,
there
Demetrius.
an easy way to see that one will hit zero as an option with that definition? Because you start by T
No,
colors and then you
no,
start.
exactly. It turns out that actually let me say yes, you could actually extend it to zero, right? Because if it's the number of proper colorings with this set, if T is zero, this set is empty. So you can't have any function.
So,
There's
sorry,
there's
no,
no there's no range.
I
What?
meant if you follow the argument that you did for T colors,
Yes,
then if we choose T more than one, then or less than three, then we will get at some point zero times zero, so it
exactly.
will be a root. But
Right.
is there any graph that t jumps from t to t minus 2 without going through t minus 1 maybe? So we don't have a root, but we have only negative parts?
No, that can't happen. So all of your roots are going to be consecutive from zero up to one less than the chromatic polynomial. To see this, remember, this coloring does not need to be surjective, right? You don't need to use all the colors. So once I have a coloring with chi of g colors, if I add more colors to my range, I can just not use them and still get a proper coloring with that range. Right? This is not necessarily an onto function. So once P of G becomes positive, it will stay positive. You will not have any more roots. Now, what is interesting, though, is this polynomial can have non-integral roots. It can have roots that are complex, really truly complex numbers. And the distribution of these complex roots in the complex plane is it's a cottage industry for people that study the chromatic polynomial. So trying to say things about where these roots will lie in the complex plane is an interesting and complicated problem. Does this answer your question?
Yeah, thank you.
Great. Any more questions about the roots? Okay. Well, one thing that's kind of misleading about this example is that P of G doesn't need to be a product of factors of the form T minus K, where K's are, where the roots don't need to all be integral. And I just said this, and we'll show you, in fact, an example where you've got real complex roots in a bit. Okay? And in fact, here is the example. Start coloring the vertices of this cycle in the same clockwise order. What's going to happen? We're going to have t ways to color u, t minus 1 ways to color v, just same argument as before. And again, same argument as before says there's t minus 1 ways to color w. But now think about x. We've got a problem at x. What's the problem at x? Well, x is adjacent to these two vertices. But we don't know whether these vertices have the same color, right? They could have the same color because they're not adjacent, or have different colors. So should I put a t minus 1 or a t minus 2 here? It's not clear. Okay, so this just going vertex by vertex method will not work for all graphs. And we're going to give you a fix for that in just a second. But everybody see what the problem is, at least for this cycle. Okay, great. So here is one of the most useful tools for proving things about the chromatic polynomial. It's called the deletion contraction law, so I have to tell you what deletion and contraction are. So G with this, I always get them confused. This is a /E, not a backslash. Is G with E deleted. You just remove E from the graph. G over E will be G with E contracted. So think of the endpoints of E as topologically and just bring them together to form a new vertex V sub E. Now, when you do that contraction, you may get multiple edges coming out because, right, things that were adjacent to both endpoints will form a doubled edge. Just replace those by a single edge so we stay in the realm of graphs. It doesn't matter, right? When we're coloring things, it doesn't matter whether there's 1 or 5 edges. We still want the vertices to have different colors. Quick example to make it clear. Suppose G is that graph and E is that edge. Then if I remove it, I get this path. And if I contract it, what happens? Well, now I've brought V and X together to this new vertex V sub E in the center. As I do that contraction, U will be adjacent to the new vertex because it was adjacent to both the endpoints here. And notice the doubled edge that you would get at U if you were doing this topologically, you just replaced by a single edge. Similarly, W was adjacent to this vertex V, and so when I do the contraction, it's adjacent to the new vertex V sub E. And if there were any vertices which were not adjacent to either X or V, they would stay not adjacent here. Clear how to do deletion and contraction? Questions? Well, here's the deletion contraction or DC lemma. Take any graph, take any edge, then the chromatic polynomial of the original graph is the chromatic polynomial of G with E deleted minus the chromatic polynomial of G with E contracted. Now, why is this a useful lemma? Well, think about it. If G has a certain number of edges, then G with E deleted has 1 fewer edge, right? Because I removed 1 edge. And G with E contracted has at least 1 fewer edge, right? And we might have even less because of the fact that you get this collapsing of doubled edges. So this is a perfect thing to use for induction on the number of edges, right? The number of edges on this side is greater than the number of edges on either of these guys or gals. I shouldn't be sexist about this. Okay, this is really easy to prove, so let's prove it. Just to give it a name, suppose E is the edge Vx. And since I'm doing combinatorics and I like pluses better than I like minuses, I'm going to prove this in this form where I bring this term over to the other side, the negative term over. So I'm trying to prove that P of G with E deleted is the chromatic polynomial of G plus the chromatic polynomial of G with E contracted. Okay? But think about it. If I delete E, then the colorings of it, that graph, fall into 2 flavors. Chocolate and vanilla. No. there are the colorings of the graph proper colorings where these two v and x endpoints here have different colors. And you can also have colorings where they have the same color, right? Because they're no longer connected by an edge. We've removed that edge. Okay, well, think about the colorings of the first type. If I color G with E deleted properly and also insist that V and X have different colors, I'm essentially properly coloring G, right? Those are all the restrictions of a proper coloring of G. To see that, let's go back to this example. Suppose I take this coloring of G with E deleted. Notice that where E was, these two vertices have different colors. Well, I can just lift it directly to G using exactly the same colors, and it's still proper. So there's a bijection between the colorings, these types of colorings of G with E deleted and the colorings of G. Well, what about the colorings of G with E deleted where you use the same color on V and X? Well, I claim that you can lift those to colorings of G with E contracted. How do I do that? Well, if these guys have the same color, then the new vertex can get that mutual color, and you can leave all the other colors the same. Right? Again, let's look at it, the example. So here's a coloring of G with E deleted, and now the previous endpoints of E are both red. So that would lift to this coloring of G over E, where, right, this new vertex has the common red color, and the other guys stay the same colors that they are. And so we're very much done. Questions about the deletion contraction law? Okay. Well, there it is again, just to remind us what it looks like. And now we can prove this theorem of Birkhoff's from 1912, saying for any graph, this is always a polynomial in T. Any guesses about what proof technique we're going to use? I think induction on the number of edges in the deletion contraction law might be the way to go. Okay, so suppose we've got n vertices and m edges. What's the smallest number of edges we could have? 0, right? We don't need any edges, just vertices running around. So that means we'll just have v isolated vertices. What does the chromatic polynomial look like in that case? Well, I color the first vertex in any of t ways. I color the second vertex in any of t ways, right? Because there's no edges to fool with, etc., etc. It's clearly going to be t to the n. Is that a polynomial in t? Last time I checked. Okay, good. So we've got the base case. What about the induction step? Well, suppose I have some edges. Pick one of them. Doesn't matter which one. As we've said before, G with E deleted and G with E contracted have fewer edges, so we apply induction to the deletion contraction law. And so on the right, we have a polynomial in T minus a polynomial in T. And last time I checked, polynomials in T are closed under subtraction. We're done. So, very, very pretty proof. Not only is this a great tool for proving things about the chromatic polynomial, it's a great way for actually calculating the chromatic polynomial. Let's go back to that cycle that we couldn't do before. And pick one of the edges. It doesn't matter by symmetry which one. So by deletion contraction, that is equal to the polynomial where I delete the edge and get this path. And if I contract the edge, I get this triangle. And now I've got two vertices where I can go vertex by vertex. Right? So for the path, right, I start at this vertex, say, t ways, and then each vertex after that as I go around the path, it's going to have t minus 1. So that will give me my t minus 1 cubed. And here, I got t ways here, then t minus 1 at the next vertex, and then t minus 2 at the... And then if I factor out the t times t minus 1, I'm left with this t squared minus 3t plus 3. Notice, this has complex roots. Just like I promised you, that quadratic, right, has a negative discriminant. So you can have complex roots for these polynomials. And there's George David Birkhoff. And that's the second section. Are there any questions? It's a good time for questions. Okay, well, as I said, I'd like to show you two examples where the chromatic polynomial doesn't seem to have anything to do with with what we're talking about, and then suddenly it just kind of poof comes out of nowhere. So we're first of all going to talk about orientations. So the orientation of a graph is a directed graph O, so that means that each edge is replaced. So think of the edge as a two-way street. Each two-way street is replaced by a one-way street, either going from U to V or V to U. And I'll use this notation for the little arrow over it. So for example, if that's my, I'm sure you're surprised to see that as our example graph. If that's my graph, here's one orientation, right? So now, rather than an edge between the two top vertices, I'm only allowed to go from this vertex on the right to that vertex on the left, and so forth and so on. How many orientations are there of a graph? A little bit of thought will just show you it's 2 to the number of edges, right? Because you're replacing each edge in one with a one-way street going one of two ways. So unfortunately, that's too simple for us to write a paper about. We'll have to think of something more complicated. And the thing more complicated that we'll think of is what's called acyclic orientations. So a directed cycle of an orientation is just a sequence of vertices such that you've got an edge between each adjacent pair and then going back to the beginning. So there'll be an edge between V1 to V2, sorry, not an edge, an arc from V1 to V2, an arc from V2 to V3, etc., and then finally an arc from VK going back to V1. Okay? Does this orientation have any directed cycles? No, it's acyclic. Right? So we call it acyclic if it's got no directed cycles. Think about it. This edge clearly can't be part of a cycle. So we could only have a cycle if we go around this triangle. But any way I try to do that, I get into problems, right? If I go counterclockwise, this edge is, that arc is fine, but this arc is not. And conversely, if I try to go clockwise, I run into problems with this arc. So this is acyclic. Everybody see that that's acyclic? Great. So let's count the number of acyclic orientations of this particular graph. Well, clearly the only place you could have a cycle is the triangle. So we could first count the number of acyclic ways to orient the triangle and then the number of ways to orient the remaining edge because it doesn't enter into any cycles. For the triangle, it's easier actually to take the total number of orientations and subtract the number of them that are cyclic. What's the total number of orientations? Well, it's just 2 to the number of edges, right? So 2 cubed. How many of them will create cycles? 2, right? Either a clockwise cycle or a counterclockwise cycle. So that's the number of acyclic ones. And I've, of course, got 2 orientations for the edge. If you give this to a Cray computer and let it crank for a few years, you might get out 12. Okay? So that's the number of orientations. Now I'm going to do something that's going to appear a little bit crazy, but just humor me. I'm an old man. So let's take the chromatic polynomial and plug in -1. Now what it means to color a graph with -1 colors, I have no idea. But just let's do it, just for fun. Right? So that I took the chromatic polynomial that we computed all the way back towards the beginning of the lecture. I plugged in -1. I did calculations and I get 12. This 12 and that 12 are the same 12. Famous theorem of Richard Stanley's from 1973. If I've got a graph with n vertices, and I plug -1 into its chromatic polynomial, I get up to this sign, the number of acyclic orientations of G. Now this is an amazing, beautiful theorem, and when I saw it, I was so awed by it that I thought, so Richard, of course, proved it using deletion contraction, because that's what you do when you... I wanted a combinatorial proof, and when I came, actually this was when I did my first postdoc at U of M, Andreas Blas, who some of you may know, the logician, I think he's retired now though, and I were then able to give a bijective proof of this theorem, which I was very happy about. Okay, so that's all I have to say about acyclic orientations. Any questions? Okay, and there's Richard and Andreas. So now I'm going to talk about hyperplane arrangements. Hyperplane in Rn is just a subspace of codimension 1. Okay? So in R3, they would just be normal planes. And then a hyperplane arrangement, script A, is just a set of hyperplanes. Pick your favorite hyperplanes. So here's a quick example. My arrangement in R, so this is going to be an arrangement in R2, so the hyperplanes are going to be lines through the origin. And I'm going to take two lines, the line y equal 2x and the line y equal minus x. So there they are. I've drawn them in the plane. I haven't drawn the coordinate axes because it'll make something later on a little bit clearer. But you can see this red line has slope 2, this blue line has slope -1, and they cross at the origin in the middle. Okay, so the regions of an arrangement, what you do is you take your ambient space, you remove the hyperplanes, and what's left breaks into connected components. Those are called the regions. Okay. So the number of regions for this arrangement is clearly 4, right? If I cut along the red line and cut along the blue line with 2 infinite scissors, then I'll get these 4 regions left over. Okay? Now you must be thinking, okay, Bruce has really lost his mind this time. I mean, there aren't even any graphs here. We're talking geometry of some sort. Hold your horses. Standard combinatorial notation, brackets n is going to be the numbers, the integers from 1 to n. Suppose we have a graph whose vertex set is labeled with the numbers 1 through n. From that, I can get an arrangement, A of g, and I get it by taking each edge. And remember, the endpoints of E are now just positive integers. And taking the corresponding hyperplane, which sets the ith coordinate equal to the jth coordinate, right? That gives you a hyperplane. It's one equation. Cuts down the dimension by 1. Let's take a quick example. Suppose this is my graph. What is the arrangement? Well, the arrangement has a hyperplane, so it's in R3, right? Because I've got 3 vertices. For this edge gives me the hyperplane x1 equal to x2, or if you prefer x, y, z coordinates, this would be x equal to y. This gives you the hyperplane x1 equal to 3, or if you prefer x equal to z. So 2 hyperplanes sitting inside there. How many regions? 4. You take any 2 hyperplanes in R3 there, it's going to cut it into 4 regions. And now I'm going to do the same weirdo thing with a chromatic polynomial. I'll take the chromatic polynomial of this, right? T for that vertex, t minus 1 squared. And I'm going to plug in -1. And out comes -4. And you probably know what the next theorem says. It's the theorem of Soslavsky's that says if I take any graph G, whose vertices are 1 through n, and take its corresponding arrangement, then plugging in -1 into the chromatic polynomial gives you up to assign the number of regions. Now, seeing Stanley's theorem and Zaslavsky's theorem back to back, you may very well be thinking there has got to be a nice bijection between the acyclic orientations of the graph and the number of regions of its arrangement. And there is. It's very pretty. I don't want to take time to do this now, but at the end of the talk, if you ask, I'll be happy to spell out what that bijection looks like. There's Thomas Zaslavsky, again, in that picture much older than he was when he proved that theorem, which I believe is in his thesis. Questions before I move on to chromatic symmetric functions? Okay, so let p be the positive integers, and suppose I've got a set of variables boldface x indexed by the positive integers, so x sub 1, x sub 2, etc. Take any coloring of my graph. With that, I'm going to associate a monomial x to the c, and you get it in the simplest possible way. Remember, you're coloring with the positive integers, which are your subscripts here. So for each vertex, take an x sub the color of that vertex and multiply those all together. That's going to give you some monomial. And then Stanley's chromatic symmetric function is just the sum of all these monomials over all proper colorings with the positive integers. Okay, this is a lot to take in, so let's do a quick example. Suppose I've got the path UVW, and I'm going to compute x of g, its chromatic symmetric function. Well, let's start really simple. How many ways are there to color this graph if I just use the colors 1 and 2? 2, right? Either I put the 1s at the endpoints and 2 in the center. That will give me a monomial x1 squared x2, right? x1 times here, x1 times here, and x2 times from there. Or I could reverse the roles. I could put the 2 at the endpoints and put the 1 in the center. So that would give me an x1 from the center and an x2 squared from the endpoints. Clear how we got these monomials? Notice this is starting to look symmetric in the sense that if I exchange x1 and x2 in this part of x of g, that remains invariant, right? Flipping those variables does not change anything. What if I use the colors 1 and 3? Well, it's going to be the same story, right? I'm going to have two ways of doing it. One of them is going to give me x1 squared x3. One of them is going to be x1 x3 squared. I hope it's pretty clear that if I use any pair of colors, I'm going to get the same thing. So I'm going to get all monomials of the form xi squared xj. Right? And that's symmetric, right? Because I've got all possibilities. Okay, but what if I use three colors? X1 and 2 and 3, say. Well, then I can put those colors on those three vertices in any way I like because I don't have any repeated colors. So any placement of those colors on the vertices is going to give me a proper coloring. How many ways are there to place three colors on three vertices? Well, 3 factorial or 6. So I'm going to get 6 colorings from 1, 2, 3 to 3, 2, 1, all with monomial x1, x2, x3. What's going to happen if I use the colors 1, 2, and 4? Same deal, right? You're still going to get 6 colorings, all with x1, x2, x4. I hope it's clear that now I'm going to get all monomials of the form xi, xj, xk, each with coefficient 6. Again, so this is a symmetric function. And it's closely connected with the chromatic polynomial. Why? Make the substitution where I let the first t variables be 1 and all the other variables be 0. What happens? This is usually denoted just by substituting 1 to the t for x. Well, this is going to kill a lot of the terms, right? Any term that involves an x sub j with j bigger than t is going to die because it's got a 0 factor. So what are the only ones that are left? The only ones that are left are going to be the ones that only use x sub 1 up through x sub t. But those correspond to colorings of v. We're just using the numbers 1 through t. And if they're all of the variables are equal to 1, well, their product is equal to 1. If I sum 1 over any set, what do I get? The cardinality of that set. So this is just the number of proper colorings using t colors. That, by definition, is the chromatic polynomial, right? So you get the chromatic polynomial back here by specialization. So I'm now going to give you an analog of the acyclic orientation theorem in the setting of chromatic symmetric functions. So we'll say that a power series is symmetric if it's invariant under its permutation of variables. And it's pretty clear that x is always symmetric for any graph. Why is that? What does permuting the variables correspond to in terms of the coloring? You're just permuting the colors on the vertices. If I take a proper coloring and I permute the colors, it stays proper, right? So it's going to be invariant under those types of operations. Bases for the algebra symmetric function are indexed by partitions, and a partition is just, so this is a partition of an integer n. It's just a sequence of numbers, lambda 1 through lambda k, that sum to n. And we don't care what order we put these in. 2 plus 3 is considered the same as 3 plus 2, so we put them in a canonical weakly decreasing order. And then these summands are called parts. So here's a partition of 10, right? 4 plus 3 equals 10, and I've put it in weakly decreasing order. Then the elementary symmetric function basis is defined as follows. E sub n is the sum of all square free monomials in my variables x that have degree n. And then to get e sub lambda, right, because we need e sub lambda for a partition, you just multiply e sub lambda 1 times e sub lambda 2, etc., where these e's are defined as from the first part. Again, let me do a quick example. What is e sub 3? Well, it's going to be the sum of all square free monomials that have 3 variables. So x1, x2, x3, x1, x2, x4, etc. All things in the form xi, xj, xk, where ij and k are different. And then to get e sub the partition 433, well, I just take e sub 4, which is just like this sum, except each monomial, each term has 4 variables in it, times 2 copies of e3. Okay, clear how the e's are formed? It's very easy. Okay, that's why they're called elementary. So the length of a partition, denoted L of lambda, is the number of parts. So for example, that partition has 1, 2, 3, 4, 5, 6, 7 parts. Okay, and to give you this analog, I need to be a little bit more precise about my orientations. So a sink of an orientation is a vertex such that all of the arcs containing V go into V. There's nothing coming out. Everything goes in. So for example, in this orientation, U is a sink, right? Both of these are going in. W is a sink, one arc coming in. V is not a sink, right? It's got an arc coming out to U, but an arc coming in from X. So here's a theorem from Stanley's original paper on the chromatic symmetric function. Take your chromatic symmetric function and express it in the elementary basis, right? That's going to give you some coefficients, c sub lambda. Then if I sum all of the c sub lambda for all the partitions that have length k, it gives you the number of acyclic orientations of G that have precisely k sinks. So in particular, if I summed all the coefficients, that would give you all possible numbers of sinks, and that will give you all possible acyclic orientations. Okay. So, any questions before I go on and talk about some comments? So I gave you watered down versions of Stanley's and Zaslavsky's theorems because, you know, when you're seeing them for the first time, it's good not to have all the bells and whistles. But let me put the bells and whistles back on just so that you see the full power of their theorems. So first of all, Zaslavsky's theorem wasn't just about the chromatic polynomial and arrangements that come from a graph. It was about arbitrary hyperplane arrangements. If you take any hyperplane arrangement, it has associated with it a certain polynomial called its characteristic polynomial. And I don't want to get into the definition of this, it would take too much time, but just believe me, there is a polynomial you can associate with it. And if that arrangement comes from a graph, that polynomial is the chromatic polynomial. So the chromatic polynomial is a very special case. So Zaslavsky's false theorem is that if I take the characteristic polynomial of any arrangement and plug in -1, again, I get the number of regions up to your sign. Also, Richards didn't just tell us about the chromatic polynomial at -1. He told us about the chromatic polynomial at any negative integer. And this is what it does at that point. Let G be a graph, pick an acyclic orientation O. Take a positive integer t and look at a coloring from t colors. Notice I did not say proper coloring, I just said coloring. And I meant that. Call the pair OC compatible if, whenever I have an arc from U to V in the orientation, it points from the vertex of smaller color to the vertex of larger color. So this is like some sort of gradient function on the coloring. So Stanley's full theorem is if I've got a graph with n vertices and t is a positive integer, then if I plug in minus t, I in fact get the number of compatible pairs up to sign. And you can get the original theorem from this by easy manipulation, which I can talk about more during question and answer period if you wish. Again, this was such a beautiful theorem that I and Vince Vader gave a combinatorial proof of this result. There's Vince. Okay, so I said I would give you an open problem. So here's the open problem. It has to do with trees. Graph G is a tree if it's acyclic and connected. So here's three graphs. Is the first one a tree? No, it's not acyclic. It's got that triangle cycle. Next one, the problem is that it's not connected. And T is a tree, right? Connected and acyclic. Easy to see that if I take any tree on n vertices and compute its chromatic polynomial, you will always get the same polynomial, namely t times t minus 1 to the n minus 1. And that's a straightforward, just start coloring the tree at some vertex t, that can be done in t ways, and then work out from that vertex, right? First of all, color each w connected to v by an edge. Since it's acyclic, there's going to be t minus 1 choices for each of those vertices, right? Because no two of those vertices can be adjacent, since they were both adjacent to v. And then just keep doing it, working outward. And that will eventually color the whole graph because it's connected. And each of those n minus 1 vertices therefore has t minus 1 choices, which gives you that factor. Okay, so that's very nice. Call graphs G and H isomorphic if they're equal once your labels are removed. So famous conjecture from Stanley, again from that original paper. Suppose we take two non-isomorphic trees and I compute their chromatic symmetric functions. They are going to be different. So notice the total opposite of this theorem. This theorem says you take two things on n vertices, always the same chromatic polynomial. This is saying take two non-isomorphic trees on n vertices, always different chromatic symmetric functions. And that may be one of the reasons that it's been so hard to prove, is because, right, how do you show that two things are always different? Well, you need to come up with some invariants of the tree that are distinguished by the chromatic symmetric function, and finding that has been a real problem. But maybe somebody in this audience will have some ideas about how to push that forward. So thanks so much for listening.
Thank you so much, Bruce, for such a wonderful talk.
Glad you enjoyed it.
Are there any questions for Bruce?
I had a question about the summing up the coefficients on the E lambdas, giving you the
Yeah, exactly. What would you like to do?
so in the case where like those coefficients won't always be positive, right? But in the case when they are all positive,
Okay.
does
Yes.
that like formula become nicer?
Yes. Okay. So you've hit a big nail on the head. So this is some sort of, in general, all we can say is that this is going to be some sort of alternating sum with positive and negative things in it. So the question becomes, when is this? There is one case I should mention where you know it's going to be positive. If the length of lambda is 1, then this, right, there's only one integer partition of n with length 1, then that's n itself. So in that case, this sum only has one term, and so therefore it's that one term is positive. But in general, you don't know. And so it becomes an interesting question of when are these coefficients positive? And this was the other major conjecture that was made by Stanley and John Stembridge, who used to be, well, is emeritus now at U of M, I should mention, was that for a certain very interesting class of graphs, these coefficients were always non-negative. And this was open for, let's see, 95 to, yeah, so we're talking 30 years. And only very recently, in the last couple of years, a proof by a Japanese mathematician, Hikita, has shown us that this is the case. And in fact, in older versions of this talk, I would sometimes talk about Hikita's conjecture because it was also very interesting. I should also say though that there is a Q analog of Stanley's symmetric function, and there is a corresponding non-negativity conjecture in that setting, and that's still open. So there's still stuff to do with that conjecture. So thanks for that question, Joseph. That was some stuff I was sad to have to take out of the talk, but it could only be so long.
I would have maybe two questions. The first question is there an analog of deletion contraction for the chromatic symmetric function?
Oh, I love you, Bailey. Okay, so the answer is no, directly. And
Okay.
how can you see this? So remember, let's go back to the deletion contraction law. Yeah. Suppose this was a chromatic symmetric function. Each of the terms in that function have degree n, where n is the number of vertices, right? Because
Mhm.
you're multiplying 1x for each vertex that you've colored. So this is homogeneous of degree n. What about this one? Still homogeneous of degree n, right? Deleting an edge does not change the number of vertices.
Yep.
What about this one, though?
Mm.
Homogeneous of degree n minus 1. There is
Hmm.
no non-trivial relationship between homogeneous of degree n and homogeneous of degree n minus homogeneous of degree n minus 1.
Yeah. Okay.
So, but we do not give up. So this is old work of mine with my former graduate student David Gebhardt. We saw this and we said, as you know, we asked exactly your question. Okay, it doesn't work for Stanley's function. Is there a way that we can make it work? And the answer to that question is yes. So what you do is rather than considering chromatic symmetric functions in variables which commute, you consider chromatic symmetric functions in variables which do not commute. And then you always list the various factors in a fixed order using non-commutative symmetric functions. One can then write down an analog of this, and then it becomes possible because you can then identify where the degree went down. There's a way to fix this, and you can use that new. So then you can use the non-commutative version to actually make so this was a long time ago before Hikita's proof. We used it to make progress on this positivity conjecture by using deletion contraction.
Great.
And you said two questions,
Oh,
or
yes. Thank you. Yes, I have one more question. So in your bijective proof of
right,
um, the equality, that if you take PG and evaluate at any negative integer,
right,
that this is
right.
equal to this number of compatible pairs. I don't remember exactly.
Right. Or we can take this simpler one, which it's a similar sort of
Yes.
thing. Yeah.
Did you, in order to combinatorially interpret both sides, did you appeal to both Stanley and Zizlowski's results, or did you have some
No, no,
different
it
interpret?
comes from a different. Okay, so there two facts about the chromatic polynomial that you need to know, which I didn't have time to talk about, but to get this bijective proof, you need them. First thing, you can notice from the chromatic polynomial up here, the signs alternate. Forget the minus one. Think of this as just a t. This has positive sign, positive sign, negative sign, etc. That is always the case. So if I plug in minus 1 and then factor out a minus 1 to the fourth here, I'm going to be also able to factor out a minus 1 to the fourth here because I got minus 1 cubed and I got a negative.
Mm-hmm.
And then this
Mm-hmm.
is positive and right. So I can
Oh yeah.
factor out the
Mm-hmm.
minus 1 to the fourth and I'm left with a sum of positive terms.
Mm-hmm.
So the only question is, why are those positive terms related to acyclic orientations? Well, it's a famous theorem of one of Birkhoff's students that these coefficients count what are called NBC sets in the graph. So what you do is you put an ordering on the edges of the graph, total order on the edges of the graph. NBC stands for no broken circuit. So circuit is just a cycle.
Mm-hmm.
And now since the edges of the cycle is ordered, I can remove the smallest edge and that'll give me a path. That's called a broken circuit. Any set of edges which does not contain one of these broken circuits is called NBC. And it turns out that these coefficients exactly count NBC, the sizes of the NBC sets by the number of edges. So what we gave is a bijection between the NBC interpretation of the chromatic
Okay.
polynomial and the acyclic orientations. There's a way to go back and forth between the two. And the one that you were asking about later is a souped up version of that proof.
Okay. Interesting. Thank you.
My
Um,
my pleasure. Other questions?
I have some questions on the last slide. Uh,
Sure.
for trees, there's always the same chromatic polynomial.
Right.
First of all, does this also seems to hold for other classes? For example, like imagine if I take
Yes.
a triangle and then some trees and some tree, I don't
Exactly.
know,
Exactly.
from the
Yeah.
triangle
This
to
is
the graph.
definitely not the only class of graphs that you could do this for.
Is there any characterization what should happen to a graph or for what classes
Um,
something like that
yeah,
holds?
that's an interesting question. I'm not sure that anybody's ever looked at that to try and give. Yeah, that would be actually very interesting if you could prove a theorem of the form that if I have a collection of graphs on n vertices that satisfy these axioms, then they all have the same chromatic polynomial. That would be very cool. That would be very interesting. I don't know of results of that type aside for the one for trees.
Okay,
You
and then
should
on
do
the
a
other
literature
side,
check to make sure.
yeah, yeah.
Go ahead.
And on the other side, the conjecture is about trees that they have non-isomorphic.
Yes. So if I
I don't
take
know how they
two,
call it.
yeah.
I
So yeah, non-isomorphic trees.
something.
So obviously, if I take two trees that are the same, if I remove the labels, then they're going to have the
Yeah.
same chromatic. But
Is
when they
there
don't, yeah.
is there a conjecture about any non-isomorphic graphs, or if you prove this about the trees, then is it easy to generalize for any two non-isomorphic graphs, or not at all?
Again, I don't know of other conjectures or statements for non-isomorphic graph families. This has been Trees are in some sense the simplest possible graphs. So
Yeah.
the fact that we can't even do it for trees is makes it a bit daunting. What has been done in relation to this conjecture is, as I kind of alluded to before, people have tried to come up with various invariants on trees that that the chromatic symmetric function knows about. That if you look at the chromatic symmetric function, you could say this tree has this invariant, and this other tree does not, and therefore distinguished in that sense. And for that, they've been able to prove this conjecture for non-isomorphic trees up to, I think it's maybe 15 vertices at this point. I'd have to go check the literature to make sure. But that's where the thrust of research on this conjecture has been. But as far
Okay.
as I know, not so much for other graphs. But again, make sure to make a literature check.
But do you believe that the chromatic symmetric function could capture everything about a graph, or is it particular for trees that?
No, no, yeah, a very good question. In Stanley's original paper, he gave two non-isomorphic graphs who have the same chromatic symmetric function.
Ah, okay.
So something special is happening for trees if this conjecture is true. It's not true in general. And these were relatively simple graphs. I think, as if I remember, they were graphs on like 6 vertices. So you didn't even have to go very far to find equality for non-isomorphic graphs. But somehow trees seem to have this weird property. So, other questions?
There is no other
There,
question. You.
no, go
Okay,
ahead.
go. Okay. Uh,
Nope.
a question also about this function. For the characteristic polynomial, there is a generalization through every poset, and there is a more general notion of characteristic polynomial, and
Exactly.
results
Exactly.
for graphs are
Exactly.
also true for other stuff. Is
Absolutely.
there any some kind of thing about the chromatic symmetric function that also generalizes in posets or?
I believe there has been a generalization to posets. Trying to remember who did it. There have been a number of different generalizations, and I've kind of lost track of all of them, or not of all of them, but because there have been so many. Again, in attempts to try and prove these various conjectures, people have, like I did with David Gebhardt, tried to look at other analogs that give you more power. I don't remember though, right offhand, if there's there what the poset generalization looks like. I mean, of course, you do have things like order polynomials, which are related, and those have multivariate generalizations as well. But for the actual coloring, and there is, again, if I remember correctly, there is a matroid version. So that's that extension has been covered. The other amazing thing about this object is that when you take the Q analog, which is due to Shereshian and Wax, there's actually connections to algebraic geometry, in particular Hessenberg varieties. There's a if they're analog of the positivity conjecture that I was talking about is true, it will tell you certain things about Hessenberg varieties, which is just kind of mind blowing. But yeah. Napur, you had unmuted. Did you have?
Yeah, I wanted to ask about the bijection with the regions in the hyperplane and the acyclic
Oh, right.
orientation.
Yes. Oh, yes. I'm glad you did that because it's so beautiful. Okay. So, so remember, each edge gives us a hyperplane. Any hyperplane gives splits space into two regions, one on its left, one on its right. Okay? Therefore, you consider orienting the edge as picking one of the two half spaces defined by the hyperplane. So if I orient the edge from I to j, we'll say we'll take the left-hand side, and if we orient it from j to I, we take the right-hand side. Okay? So now to every orientation, acyclic or not, we have, what have we done? For each hyperplane in my arrangement, I've picked one of the sides. Okay? It turns out that if the orientation, so what can you associate with it? Well, you can associate with it the intersection of all of those half spaces. Right? You've gotten a half space for each edge and for every hyperplane. So you've essentially taken a bunch of half spaces and let that correspond to its intersection. It turns out that the intersection of those half spaces will be an actual region, right? The intersection of those half spaces, since you took one for every hyperplane, will either be a region of the arrangement or it will be empty. The intersection of those half spaces will be a region precisely when the orientation is acyclic. And therefore, that's why the acyclic orientations correspond exactly to the regions. Yeah, it's very, very, very cute. Very, very cute. Thanks.
Thank you.
And why don't you miss any region through that?
I'm sorry, say what?
How do you prove you don't miss any region through that?
Because each region can be defined. Take a region, look at each hyperplane. That defines a side of the hyperplane, right? The side of the hyperplane that the region is on, right? So given a region, you now have picked a side of each hyperplane, and that's why it's onto. Yeah. Other questions? Okay, well, these have been great questions. Really, really nice.
Thank you so much again, Bruce. Let's thank Bruce one more time.
My pleasure.